Hello, everybody. This is Gigi. In this video, we will be talking about limit of sequences and limit laws. Okay. We're going to start with the sequence here, the sequence of AN going from 1 to infinity. And the equation for that is N over AN is N over N plus 1, right? So if you look at the equation here, it looks kind of like the function, right? So we know that the sequence is a bunch of dots there in pink, and it behaves like the function f of x equals to x over x plus 1. So we can say here, if we think about it, that the limit as f of x goes to 1. Therefore, our sequence should also go to 1 because the sequence would be those pink dots there that's following that black line. So yeah, it's going to go to 1 as well, right? So algebraically, we can loosely use the notation like we would with functions, meaning saying the limit as n goes to infinity of n over n plus 1. Well, and since it's is behaving like a function, we would say that we could apply limit laws. And L'Hopital rule is one of those that we have learned that is very useful. So because this is infinity over infinity, which is one of those indeterminate form that we know, and that L'Hopital rule will apply, we can go ahead and take the derivative of the numerator and a derivative of the denominator. So that would be the limit of 1 over 1, which is 1, just as we have seen here in the picture, right? So again, AN, the sequence AN converges to 1, okay? The concept here that we need to pay attention to is that it behaves like a function. So we can loosely use function notation like we have before when we are taking limits, okay? So let's look at this sequence here. AN is 1 and then 1/2, and then 1 over 5, 1 over 10. And if you stare at it long enough, you would probably realize when n is 1, A1 is 1, right? 1 is like 1 over 1. Do we want to say AN or do we want to say A sub 0? So I think I kind of now see a little pattern. So say A sub 0 is 1, meaning when n is 0, A sub 0 is 1. When n is 1, then A sub 1 is 1 over 2, right? And so on. So this is when n is equal to 0. When n is equal to 1, this is when n is equal to 2, and this is when n is equal to 3. Are you seeing something yet? What's the next term in the sequence if we had to write it down? The next term in the sequence, I think, is going to be 1 over 17 when n is 4. Are you seeing it yet? I would say that you have, and that the equation for that, the formula for that would be AN is 1 over n squared plus 1, right? All right, now is this sequence going to converge or diverge? Well, let's take the limit, okay, as n goes to infinity. When we ask, is it going to converge or diverge, we want to say way out there in the sequence. Is this number going to approach some, is this sequence going to approach some number? Okay, so here is the graph of how that would look like. And the dots are the sequence terms, and the red line or curve is the function 1 over x squared plus 1. So you can see again that the sequence behaves like the function. So we would say, let's take the limit as n goes to infinity of 1 over n squared plus 1. And when n is going to infinity, this is a big number. So 1 over a really big number is going to approach 0, as you can see on the graph. So we will say then that the sequence an converges to 0 in this case. All right. So as we said, the sequences behaves like the associated functions. So all the limit laws that was true for functions would be true for sequences as well. Okay, so you get the sum, right? Limit of a sum is the sum of the limits. Limits of a constant multiple, you can pull out the constant. Limit of a product is the product of the limits, and also a quotient as well, as long as the denominator is not 0. All right. Now talking about limit laws, let's apply that to this huge sequence n here. Okay. Now, looking at this, we can think of, oh, I think we can break this apart like so. Here is 1, right? So I see that this sequence, Cn, is a product of An and Bn, where An is 1 over 2 to the n power, and Bn would be the rest of it there. So if I can show you that this converges to a number and this converges to another number, then I can conclude that the limit law will hold and that the sequence will converge to the product of those limits, right? So go ahead and say, let's take the limit as n goes to infinity of An. Of course, that would be 1 divided by a big number, and that would go to 0. For the second sequence, we use that nifty little trick and divide everything by n squared. That's the highest power, right? We learned that in Calc 1. And we will get the limit being, this is going to go to 0, this is going to go 0. So what you have left is 2/3. So we would say that the limit of Bn would go to 2/3. So the limit as n goes to infinity of Cn, since C is made up of two sequence, An and Bn, then the limit would be the product of those two limits, which would be 0 times 2/3, and that is 0. So just as usual, limit laws for functions will apply here for sequences as well, which bring us to the squeeze theorem, right? The squeeze theorem. If we are looking at the function, not function, the sequence Bn that is always falling in between the blue one and the pink one there, the blue being Cn and the pink being An. If Bn is always going to hang out in between those two, and we know that An converges and Cn also converges, both converge to L, then B is going to have to converge to L. That's what the squeeze theorem said, right? If you're going to always be hanging out between these two friends here, and these two friends are going to go into whatever place they're going to, and hopefully that's a good place, then you are going to also gonna be right there with them, okay? That's what the squeeze theorem said. Now, how do we use it? Suppose you are considering this sequence Bn is equal to cosine of n over n squared plus 1, right? All right, so what do we know about cosine? We know that cosine is always going to be in between -1 and 1. Divide everything by n squared plus 1, we will have the sequence in the middle is our Bn. Okay, now our job is to show that the left and the right are going to the same place so that our sequence in the middle is going to also go to that same place as well, right? So let's consider first the one on the left. We would have -1 divided by a big number. That would be a negative, very, very, very small number. So we would call that 0. On the right, when n goes to infinity, we have 1 divided by a big number. That is a positive, very, 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 very small number. And we would call that 0 as well. So these two converges to the same number 0. And our sequence Bn is always hanging out in between those two. So we would say that our sequence Bn will have to converge to 0 as well. And that is how the squeeze theorem works for sequences. Okay, some terminology here. I want to focus on this one right here. Non-decreasing means the an plus 1, the next term is always going to be greater than or equal to the previous one. That is, so we call that non-decreasing. It's not decreasing, right? It's either going to be the same or higher. And then non-increasing means the n plus first term is always going to be less than or equal to the nth term. So if a sequence is either non-increasing or non-decreasing, we call that a monotonic monotonic sequence. See how I always get these things confused because they behave the same way. Monotonic sequences are either non-increasing or non-decreasing, meaning it just moves in one direction, right? And then another definition that we want to look at is bounded. What's the word bounded? Well, you guess it. It just, you know, that would be the maximum or the minimum, right? If it has that, it's bounded above, if there's a number m that all of your sequence terms, no matter how far out you go, it's going to be always less than or equal to m. That tells you that your sequence is bounded above, right? Or the other way around, if there's a number n where your sequence term is always going to be greater than or equal to, then your sequence is bounded below. Okay, so, and if it's bounded both above and below, then you would say the sequence is bounded. Okay, so if it's not described above or below, we really mean it's bounded by both. Okay, now, a theorem that is almost as critical as the squeeze theorem in limit law for sequences is a theorem that will say this. Okay, let's just kind of take a look here and digest the information, the terminology that we just went through. The red is a decreasing bounded sequence. The black is an increasing bounded sequence. You see how that looks like, right? So both of these are what we call monotonic sequences, right? Both of these sequences are monotonic because it's moving in just one direction. Okay, so it's like this one just kind of goes down like this, and this one just goes up like this. It's just go in one direction, and that is monotonic. And the theorem, as I mentioned that is almost as critical as the squeeze theorem is the BMS. BMS, not PMS. That's PMS is what I do. BMS is what sequences do. BMS converges, meaning a bounded monotonic sequence converges. And that's a theorem that has been proven. And we are able to use that to prove that sequences converge using this theorem. As long as we can show that it's bounded and that it's monotonic, then we would say that the sequence has to converge. Okay, that is it for now. And in the next video, I will show you how that BMS theorem works.